study the universe, the contents of the universe, how everything evolves, how everything interacts, basically everything inside the universe. It's a great thing to study. I really love being able to unmask the secrets of the universe and study dark matter and black holes and crazy things like this. And I love talking about what I do. I love sharing science with everybody. So the purpose of this broadcast is to answer any questions you guys have about the universe, contents of the universe, basically any questions you want to ask. Also, what it's like to be in academia, what my research is about. This isn't Ask Me Anything, so you can go ahead and ask me any questions. I will try to answer. Hey, Abyss, nice to see you as always. Thank you. Thanks for joining, and thanks to all the regulars for stopping by, and hello to anybody new. If you still follow me on Periscope, you want to head over to Happs. Happs is where all of my broadcasts will be hosted in the future. Really loving the whole Happs platform, really nice platform here. So if you still follow me on Periscope, you want to head over to Happs in the future, because as you know, in 2 months, Periscope will no longer be around. So the objective here is to answer any questions you people have. This means you ask questions, so I try to answer. But just to get things rolling and to start a bit, I want to talk about what is one of the biggest space events happening this week. And of course, I'm talking about the Mars 2020, the Mars landing that we get tomorrow. Tomorrow afternoon, or afternoon, evening, depending where you're based, another rover is going to attempt to land on the surface of Mars. So far, only 4 rovers have been successful at landing on Mars. So far, we've had Sojourner, we've had Opportunity, we've had Spirit, and we've had Curiosity. Tomorrow, Perseverance is going to attempt to become the 5th to land on the surface of Mars. Now, this is a ridiculously difficult mission. Overall, only 40% of Mars surface missions are actually successful. So there's a high chance that things could go wrong, but we're very hopeful that things will actually go right. So the image you can see here on the screen next to me is an artist's rendering of what Perseverance will look like once it's landed on Mars. And this is really, really exciting. This rover is going to do a lot of really cool science, assuming it gets there. Because first it has to go through what is known as the 7 minutes of terror. So the 7 minutes of terror is the landing process for this rover. It's the same process that Curiosity went through. And this is a 7-minute descent pattern where lots of things have to go right. Everything has to happen in a precise order. Now here's what makes it even harder. Given the distance, the current distance to Mars, any signals we send to and from Perseverance take 11 minutes to get there. So there's this 7-minute landing process that this rover has to do without any help or without any guidance. The experts working on this mission can send signals up until not long before the descent, but once the descent starts, it's on its own. And it has to manage a 7-minute descent without any outside interference, because we wouldn't be able to send signals to affect it. Now, if it lands, I will go into more details about the landing process in a minute, but if it lands, it will have 4 main science objectives, really cool science. I should mention that it's going to land, assuming everything goes correctly, it's going to land in the Gyros Crater. This is a crater on Mars that used to be flooded with water. So this is a place where there's a higher chance of finding hints or signs that Mars used to be habitable. Is where we might find any hints or signatures of any microbial life that used to be on Mars years and years ago. So what this rover is going to do, if it lands, its first mission is going to be to look for habitability, to ask the question of, could Mars ever have been a habitable planet? Could it ever have hosted life? Now, the second question that this mission hopes to answer is, are there any biosignatures? Are there any direct evidence or direct hints that there used to be any type of life on Mars? Microbial life, tiny little thing. This is the second science goal. The third science goal, which is personally something that I find extremely fascinating, is going to collect samples of the dirt, of the gravel. It's going to do some analysis there. But of course, ideally, we want to bring these samples home, because there's so much more we can do in a lab on Earth than what we can do with a rover on Mars. So Perseverance, Percy, assuming it lands successfully, will also scut around the planet and collect samples and put them in little tubes. It's then going to leave little deposits, like here's a stack of tubes, here's another stack of tubes, with the objective that in the future, another rover will go to bring these back home. So then in about, I think it's 10 years from now, the plan will be to launch another rover and orbiter combination The rover will go around, collect all of these samples, and shoot them up to the orbiter. This orbiter would then bring them back home and deposit them on Earth. So Perseverance is going to start the first step of bringing home Martian samples. Soil sample droppings, that's basically what it's going to be doing. It's going to be picking up a bit of soil, a bit of dirt, a bit of rock, putting it in tubes, and hoping that in the future another robot can throw them up into space, an orbiter can catch them and can drop them down on Earth. And this is incredibly ingenious. The fact that we've come up, or not we, I'm not involved in it, but the fact that people have come up with this idea, this proposal of how we're going to get Martian rocks back home that requires 3 different experiments, and it's such an involved process, and it's really amazing. The 4th mission and 4th final objective is actually going to be helping prepare for a future human-based Mars mission, a crewed mission to Mars. One thing that Perseverance is going to test is the ability to produce oxygen on Mars. It's going to input the carbon dioxide that's present on Mars and see if it can produce oxygen and how this works and what quantities. So there will be the oxygen production test on the rover as well. And if all of this wasn't cool enough, all of these science objectives weren't cool enough, Perseverance is also taking a companion with it this time. It has a baby helicopter or drone, which is known as Ingenuity. And this is basically going to be a little helicopter that's going to pop out of Perseverance, fly around a bit and land again. It's going to pop out and go down. So this is really, really cool. It's going to try to do this about 5-6 times over a 30-day period, I believe. The flights won't be much higher than 10 meters, just go up a bit. It might go around the rover. And this is also partly to test different flight capacities, different engines, different systems on Mars. So there's going to be Perseverance with its little baby helicopter friend, Ingenuity. So this is absolutely amazing. I'm really, really looking forward to seeing this launch tomorrow. Now, this is something that has been done before, most recently by Curiosity, I believe in 2012. Curiosity is still around on Mars. There's no chance of these rovers meeting because Perseverance will be on one side of Mars. Curiosity is quite far away. So you're going to have these 2 different rovers. They're still doing amazing science. And when Curiosity landed in 2012, there were some issues that happened. For an example, they noticed that the wheels degraded faster than they expected because of the rough Martian surface. So Perseverance is building on everything that Curiosity taught us. It's building up on this knowledge. Perseverance will have better wheels, it will be better equipped to deal with the Martian surface. And also one new thing that it has is many more cameras, many more sensors, and a better ability to actually record all of its surroundings. As Abyss is just pointing out, Perseverance also has microphones to pick up on the noise around Mars. It's actually going to be listening to Mars. There is also a very sophisticated weather station that's going to measure every possible variation in the atmosphere. There's a lot of different experiments and instruments on board Perseverance itself. Let me just bring up a second image here instead. And I'm just going to briefly put this one into hero mode. I love hero mode here. So you can see here just an overview of the different individual instruments on board of Perseverance. You can see here there's the weather station, there's X-ray cameras, there's interferometers. There's so many different parts here. There's a mechanical arm that is 2 meters long with some cameras at the end called Watson and another device at the end called Sherlock. Very good at naming things. You think the soil samples are kind of silly? If they still have to send something to get them, why not have that vehicle collect them? The main reason there is because of the different functionalities and the different tasks. So, for an example, Perseverance is equipped with baby drills, so it can actually take samples that are not necessarily on the surface. Now, these are different instruments that you would need to actually package these up and ship them up. So the next mission would be purely focused on collecting them all and then shooting these up into orbit, and that requires a huge effort to actually get these capsules back into orbit. It's not something that Perseverance can do, and likewise a future mission wouldn't have the technology that Perseverance has to actually dig up these samples, do the first analysis and package them properly. So you do need both working hand in hand. Ideally, of course, you want one rover that does everything, but this becomes extremely pricey and extremely heavy. The heavier the rover, the harder it is to transport. So Perseverance is already 1 ton. It's just over 1,000 kilos. It's about the size of a car. And this to me makes it even more incredible because we've essentially thrown a car-sized rover that weighs a ton at Mars, and we have to land it in a crater that is 45 kilometers across. That's 28 miles if you use the weird system. That is a really small bullseye that we've got to get this rover in. This is incredible that we're even attempting. I say we, I'm in no way involved in this mission. Full disclaimer here, I'm just super interested in it, but I am in no way involved in any of this science. But we scientists, we humanity, have thrown this robot at Mars at a really small bullseye, and we're hoping that it's just going to land there and land properly. This is amazing. I love talking about the Mars lander rover. The Mars lander and the rover. So I just want to go, of course, if you have any questions about what I'm discussing, please ask me. I know there have been some questions about other topics as well. I will come back to those other questions later on, like primordial black holes, postdoc life. I will come back to those later on. First, I want to focus on Perseverance a bit. Feel free to ask any questions. I will read them all afterwards. So the most fun part of tomorrow's event is the landing. Now, the landing itself is going to be rather difficult. Let me just find the exact image here, and I'm also going to put this one to hero mode once it's loaded. So, back to the 7 minutes of terror. What happens in the 7 minutes of terror? About 10 minutes before these 7 minutes, so 17 minutes before touchdown, the capsule containing Perseverance is going to kind of start entering the atmosphere and slowing down slightly. At this point, well, it's going to hit the atmosphere, sorry. When it hits the atmosphere, it's going to be traveling at 20,000 kilometers an hour. It's then going to have, this is a period at which no more signals can be delivered, now it's on its own. Then it's going to gradually start plummeting through the atmosphere. Once it starts, 10 minutes before it enters orbit, then 17 minutes before the final touchdown, or 10 minutes before the 7 minutes of terror starts, it's going to enter orbit. 10 minutes later, the 7 minutes of terror start. At this point, it enters the atmosphere properly. Now, this is when it's going to be traveling at 20,000 kilometers an hour. As it crashes through the atmosphere, so we know that Mars's atmosphere is a lot less dense than Earth's atmosphere. It's like 1% the density of Earth's atmosphere. But it is still enough to create substantial friction. And friction has a tendency to heat things up. So as this capsule is crashing through the atmosphere, it's going to be heated up to about 1,300 degrees Celsius, which is ridiculously hot. Now, of course, the rover itself, all of the science inside, cannot withstand these temperatures. So there is a really good heat shield on the outside, which is going to absorb all of this heat if everything goes to plan, and keep Perseverance safe and maintained at a good temperature. So this is a really important part. This heat shield cannot fail. Now, once this is slowed down to more manageable speeds, what's going to happen is a parachute gets deployed. This parachute is really going to help slow it down more. It's going to position it properly. It's going to slow the descent. About 20 seconds after the parachute is deployed, it's going to drop its heat shield. This will land somewhere on Mars close by. It will drop its heat shield, and then the rover itself is exposed to the Martian atmosphere. And this is where there is one big difference to what Curiosity did last time. So when Curiosity did this, there was nothing that could be done. If something was going wrong, it's going to go wrong. If it's on a collision course, it's going to crash. Perseverance, on the other hand, has some sensors. It has some tracking information, which is actually going to check the surroundings. So by now, they've given to Perseverance a super detailed 3D map of the surface of the planet. It knows what to expect in its general area. As this approach happens, the rover itself is going to map out the region and check that it's on the right course. If it's about to crash into an obstacle, it can postpone slightly the very next stage, not by a lot, there's a very small window. But it does have these sensors inbuilt that make it a bit easier to track what's happening. It also has super nice cameras that are going to, once the heat shield is deployed, the cameras are going to switch on and record this whole process of what comes next, which we didn't have before. Now, obviously, we will not see these images live. There is an 11-minute delay between signals they're reaching us, and any images we see will be slightly cleaned and processed before we get them. Now, once it's decided that everything is kind of on track and that it's set to land, it will slow down enough to the point that the parachute can be disconnected. The parachute goes away. And at this point, the sky crane happens. So they gradually lower out the rover from the capsule. There's going to be this crane that's going to guide it down to the floor, slow it down enough, and basically gently deposit it on the surface. Once Perseverance is gently deposited on the surface, and we're talking about a 1-ton rover the size of a car that's going to be slowed down with parachutes, and then a sky crane just going, no, let's just put it here. Once this happens, the sky crane, once it confirms, yep, we've landed, everything's okay, the sky crane is disconnected and it goes away. The sky crane will then do a safe crash somewhere else on the surface of Mars that shouldn't affect any of the science ongoing. And then Perseverance is safe on Mars if everything goes to plan. I really can't emphasize enough how much could go wrong here. There are so many things that could hinder or prevent this landing from being successful. This is a huge step. It's a huge science procedure. The landing is scary. And even after it's landed, it will still take us 11 minutes to know that it's landed safely on Mars. This is not only the 7 minutes of terror for the robot, but also for all the engineers and scientists who have poured hours of their life and weeks and days and months into this experiment. And now they just have to wait and hope and pray and hope that for the best. And I'm very glad that I'm not directly involved in this, because my anxiety level cannot deal with it when I'm not involved with it. So if everything goes well, the rover will land at about 10 o'clock Central European Time tomorrow evening. That's 4 o'clock Eastern Standard Time. If you want to follow this whole spectacular process, NASA will be doing live streams about it. The live streams start at 2:15 Eastern Standard Time. That's 8:15 Central European Time in my time zone. There will be a lot of build-up. Everything I've just explained will be explained in much more detail with many more experts talking, discussing all of the aspects. And if everything goes to plan, tomorrow at 10 o'clock my time, 10 o'clock Central European Time, we will have the 5th rover on Mars set off to do some amazing science. Let's assume that it lands and everything goes to plan. It's expected that within the next few days, NASA will actually release the full video of the landing as soon as the heat shield is deployed. This is footage we've never seen before with any of the other rovers. So if we get this footage, this is absolutely amazing. And it's going to be spectacular to see this whole process. So tomorrow, if you follow anybody who's in science Twitter, tomorrow Science Twitter will be talking about one thing and one thing only, and it's this Mars landing, because we have every reason to be excited about this. As Joel just pointed out in the comments, it's a multi-stage landing. Every stage introduces additional chances of failure. Only 40% of Mars surface landings have been successful so far. There's a lot that could go wrong, but also it could go right. We could succeed. And, the robot is called Perseverance because this is what humanity has done to get here. We have this perseverance to get to Mars, to try these landings, to attempt the impossible. Maybe we'll succeed. They succeeded with Opportunity and with Spirit and with Sojourner and with Curiosity. So now Perseverance has to join them on the surface of Mars. I'm very excited about this. I hope I've convinced you that this is interesting and worth following. And I really hope you'll all tune in tomorrow to follow the landing, because it's going to be amazing. We won't get images and we'll just wait for the bleep in the data to show that it's landed successfully. But if it does land, it will be amazing. And I also just want to point out that even if it doesn't land, it's still amazing, because even failure in science can be extremely good. If something goes wrong, we will get a lot of data, we will get a lot of information, we will get a lot of telemetry, which will help us try again. So not every scientific experiment ends in dramatic success. Some don't. But even if an experiment goes wrong, you can learn a lot from it. It can move science forward. Of course, we're all hoping that it goes right. But if something goes wrong, we don't have to give up and say, okay, that's it, we're not going to Mars again. If something goes wrong, bad luck, it can happen, it might happen. But if nothing goes wrong, it's going to be amazing. It's going to bring us so much more cool science. Sojourner went in a bouncy ball. This thing has rockets and cables that need to be snipped at just the right time. It's a lot harder, but it's also a lot bigger, a lot heavier, and contains a lot more science instruments than Sojourner. Sojourner was pioneering at the time. The delay in receiving data is 11 minutes. So it takes 11 minutes for any signal we send to reach Mars and 11 minutes for any signals to come from Mars to us. So by the time we get the signal saying that it's entered the atmosphere, it's actually already landed, hopefully, or it's crashed. There are these 7 minutes of tail, these 7 minutes process for the landing, and it will take us 11 minutes to know that everything is going to plan. So we watch everything or follow everything with an 11-minute delay, which is why scientists cannot intervene at this point. The robot's on its own, the lander's on its own. We hope for the best, and we wait and see, and we hope that this 1-ton car that we sent at this 45-kilometer crater actually lands exactly where we hope it to land. And we wait 11 minutes because there is an 11-minute delay. Okay, so I hope I've just been able to briefly convince you that this is a super exciting process that's happening tomorrow. You can tune in live. Of course, this is not a crewed mission, and if something goes wrong with an uncrewed mission, it is not as catastrophic as if something goes wrong with a crewed mission. Fortunately, there haven't been any serious issues with crewed missions lately. Historically, there have been a lot. Space is difficult. Space travel is very, very challenging. The people who put their lives on the line to go up and explore the next frontier to take us further are absolutely incredible and amazing. And full credits to anybody crazy enough to launch themselves into space. On that comment of people crazy enough to launch themselves into space, just should mention that the European Space Agency has just announced their new call for astronauts. There has not been a call for astronauts in Europe in 11 years. They've now announced that there is a new call for astronauts starting essentially now. Applications open March 31st, they close May 28th. 2-month application period, then 18-month consideration process. But if you're a member of a European state or if you're a citizen of a country that's a member of ESA or contributes to ESA, and if you meet the minimum requirements, you can now apply to be an astronaut for the European Space Agency. Many people say you only get one chance in your life to apply because these calls come out every 10 years and there's some age restrictions, so it's unlikely that it can happen that it might coincide that you can apply twice or 3 times, but normally it's a once-in-a-lifetime chance to apply. So if anybody here is in Europe and wants to become an astronaut, now is the time to check the criteria and to see if you're eligible. The criteria are not as harsh as you might expect initially. Of course, then they're going to order 10,000 applications for about 5 positions. It's going to be tough. It's one of the toughest selection processes there is. But if you're interested, you have to give it a go, because why not? What do you have to lose? So why the call for astronauts now? That's a nice question, and it's actually something they addressed in the press conference yesterday when announcing this new call for astronauts. Why the call now? And the answer would be, why not? It's always a good time to recruit new astronauts, but the actual arguments they gave, on the one hand, any new astronauts also need to learn from the existing astronauts. There does need to be some overlap. You can't wait until your existing astronauts are no longer working on missions to get in new people. There has to be this overlap. And there's also a lot of exciting plans. Of course, the International Space Station is there. It's the destination currently. There's also plans for potentially a moon mission, a Mars mission. There's all of these future plans that do require a new generation of astronauts. Anytime they bring in a new generation, it's a lot of lengthy training. It's several years until any of them is actually space ready or ready to be sent up on a mission. So having this overlap with existing astronauts is extremely positive. You can pass the knowledge on from the current ones to the new ones. You can merge everyone together. It's a good time to open a call for astronauts. And the director of the program was asked exactly this question, and his response was, why not look for astronauts now? There's no reason not to. And I like that mentality, and I think it's really, really amazing that there is now a call for astronauts. I know people that are applying. Of course, the obvious question there of, am I applying myself? I am honestly not sure. I really don't know. I need to think about it. I'm not sure. On the one hand, going to space is amazing. Like, who wouldn't want to go to space? On the other hand, maybe, I'm not sure. I will know in a month if I'm applying or not. Have to think about it. But, you know, there's, what have you got to lose? Apart from a bit of time doing your CV, your medical test, preparing everything. Seems like it might be worth doing. But I honestly cannot give a clear answer to that question because I don't know the answer myself yet. I've been thinking about it for a few days and I'm still no closer to figuring out the answer to that. Okay, so now I'm going to go back and address some of the questions that I ignored from the beginning. As always, if you have questions, feel free to ask. I wanted to start with an introduction about this big thing happening tomorrow, but really I'm happy to answer any questions you have about science, about my research, about what we've discussed, about random topics. Just if you have anything you want to ask away. If it's a question I don't want to answer, I'll just tell you I don't want to answer. So there was a question from Abyss of how is a postdoc life compared to your PhD? And that's a bit of a tough question to answer currently, mainly because I started my postdoc in October. So I graduated from my PhD, completed, became a doctor, end of September last year. And I started my postdoc in October. Moved to Belgium, started my first postdoc. And then in March, everything locked down, March last year. So I'm 16 months into my postdoc. And I spent 10 months of those in lockdown, working from home, barely seeing my colleagues. You know, it's really not fair to judge the postdoc experience based on the postdoc experience in lockdown. So I only really have the first 4 or 5, 6 months to judge that on. And it was definitely different. On the one hand, I felt like I had fewer things to be concerned about. You know, in a PhD, you always have the overhanging thing of you're going to have a thesis to write, you're going to have the examination, you're going to have this big thing to do at some point. And in many regards, you're still a student. And when you change to postdoc level, you get a bit more freedom. You no longer have this big overhanging task. Instead, you do have the thought of applying for the next position, filling out your CV so that you're more attractive to future places. So I think the stress comes from different places. I would say the stress levels are slightly less as a postdoc than as a PhD, but the stress comes from different places. And then it also very much depends on the group you're working in and what type of supervising you have. Some supervisors like you to work on very specific topics and you're hired to work on one thing. Other supervisors hire you to work on whatever you want as long as you collaborate with them. In my first postdoc, I was in the second category, so it's like work on whatever you want, we'll collaborate. So that's also very nice because I was able to wrap up a lot of projects from my PhD. So I was able to wrap everything up. And I think it was really, I was just really starting to appreciate the postdoc style and the differences, and then the lockdown happened, and since then it's kind of hard to assess because, you know, I can't judge a postdoc experience having spent 10 months barely leaving the house. We are in lockdown. I leave the house to go shopping and that's it. Haven't met with friends in a very long time. So it's very hard to judge the postdoc lifestyle based on that. It's actually quite interesting because in a few months I will be moving on to my second postdoc. My first postdoc was intended for 2 years. And it's very strange to think that probably 3/4 of my first postdoc will be spent in lockdown. Hopefully I will actually get to see my current office at some point again. But yeah, it's definitely not the way I envisioned my first postdoc being. But I don't think anybody really anticipated this pandemic, at least not to this level. Okay, there's a question that apparently was held over last time. I didn't answer it last time. Any new work on primordial black hole theory? So there's a lot of work on primordial black holes. I'm currently not working on that topic myself. I have briefly worked on primordial black holes in 1 or 2 papers. Now, just so everybody's on the same page here, there are 2 main types of black holes. And normally when we talk about black holes, what we think of is a star that's reached the end of its lifetime and it's collapsed. Once a star reaches the end of its lifetime and collapses, if the pressure and density are enough, it can form a black hole. These are the black holes we usually think of, collapsed stars that go supernova and leave behind this remnant at the center. But there's another type of black hole which is known as primordial black holes. Now, the idea behind primordial black holes is that they're formed in the very, very early universe, before the first stars began to form. And these primordial black holes are formed when the region of space-time is so dense that itself can collapse. You don't need hydrogen or helium like you have in a star. You just have this region of space-time that is so dense that it collapses into a primordial black hole. Now, these primordial black holes are very, very interesting because depending on their properties, they could account for a bit of dark matter, maybe all of dark matter. This is still up for debate. It very much depends on the assumptions you put in as to how the primordial black holes were created exactly. You can make primordial black holes account for some of the dark matter, all of the dark matter, or none of the dark matter. In this topic, there's a new paper every week with new ideas of, hey, here's a new idea of primordial black holes accounting for dark matter. So there is definitely research being done into that. There's also a lot of research being done into how exactly these primordial black holes would form. And this is very much tied to an early period of exponential expansion in the universe known as inflation. Now, the properties of inflation can actually give, depending on how inflation took place, if it took place, we assume it did, it might not have done. If inflation took place, depending on the exact nature of inflation, how long it lasted, what caused inflation, it can give rise to different sets of primordial black holes, or different families of primordial black holes. So, of course, then there's a lot of interest here as to what we can learn about inflation with primordial black holes. So that's an ongoing field in terms of primordial black hole research as well. Also, in terms of primordial black holes, they gained a lot of attention recently with the LIGO-Virgo measurements. Now, LIGO and Virgo are these detectors of gravitational waves. Any cataclysmic event in the cosmos, such as two black holes smashing together, two neutron stars merging, a black hole and a neutron star merging, all of these events are big enough that they would actually create ripples in the fabric of space-time itself. These ripples would propagate outwards, really, really, really tiny ripples in the fabric of space-time. We now have the technology to detect this here on Earth, which is absolutely incredible that we can detect these tiny, tiny, tiny fluctuations. Just to put it in perspective here, if two black holes merge, they come together, they merge, they produce gravitational waves. These gravitational waves, by the time they reach you, if one gravitational wave passes through you, it would make you grow or shrink by a billionth the width of a human hair. So if you take a human hair, you divide that into a billion. I'm not talking lengthwise, like widthwise. You divide that into a billion. That is the impact a gravitational wave would have on a human. So this is an incredibly small effect. And we have built these huge machines, these huge laser interferometers, where we use a laser bounced back and forth off of a mirror to measure these tiny, tiny, tiny differences in distances. This allows us to trace back the origin of the gravitational waves. We've now found gravitational waves coming from merging black holes, from merging neutron stars, from merging black holes and neutron stars. And this is really, really amazing. We are just starting off with gravitational wave astronomy. We are the first generation of humans ever to have access to this type of information. It's still a field very much in its infancy. It's still a field that is very much growing every week. We don't even know yet everything we're going to discover with gravitational waves. There are so many things that we can learn with gravitational waves. It's a whole new way of looking at the universe. I will get back to primordial black holes in a second. So these gravitational waves come from merging black holes. We can use them to trace back how big were these black holes that merged. We have gravitational waves, we detect them, we know they came from merging black holes. Now we can ask the question of how massive were these black holes. And here's where it gets very interesting, because we have a lot of different classifications of black holes or different predictions as to what size black holes should be. And some, not all, but some of the black holes that were found by LIGO-Virgo, these gravitational wave detectors, are slightly different mass range, slightly smaller than what we expected. And this raised the question of, did LIGO and Virgo actually see primordial black holes? Was it the merger of two primordial black holes and not gravitational waves? There is not a clear answer to this question. There are new papers every week, some saying it's primordial black holes, others saying it's normal stellar black holes. So I know this is a very long answer. The question is what's going on in primordial black hole research kind of thing. So we're still trying to figure out if primordial black holes exist, the origin, if they can account for a fraction or all of the dark matter, and if LIGO and Virgo measured primordial black holes. Then there's other things you can do of using, for example, the galaxies around you, the way galaxies distort, or in fact, any huge burst of energy that could indicate an evaporating primordial black hole. You can use all of these observations to put bounds on what type of primordial black holes there could be, how massive these would be. These are all things we can constrain just by looking around at the universe. So I know that was a long answer. The question was what's new in primordial black holes, and the answer is really a lot. There's a lot going on in primordial black holes. It's a really hot topic and a really interesting topic. And thanks to observations from LIGO and Virgo, we might actually be able to gain more information about primordial black holes. Okay, I know that was a very long answer there. I hope I didn't lose anybody. As always, any follow-up questions, any clarifications, feel free to ask away. I noticed there's somebody that being very disrespectful in the comments. If you're going to take that attitude, I'm just going to completely ignore your questions because I don't have to deal with that. Okay, what does gravitational wave astronomy aspire to accomplish? With the current settings of LIGO and Virgo, can we detect black holes, large or small, occlude an incoming gravitational wave? So what we hope to accomplish is to, on the one hand, understand these objects more. We hope to understand black holes more. We hope to understand neutron stars more. We hope to understand black hole neutron star mergers. This is something, it's always the question of how do you study a black hole? A black hole doesn't emit light. The only way you can normally study a black hole is by looking at its impact on other objects close by. Whereas now with gravitational wave astronomy, we can actually gain information on the mass of these black holes, their spin, depending on how much they were spinning when they collided. So it opens up a whole new window into black hole information. But then there's also some other really cool things you can do with gravitational waves, especially for an example, if you get gravitational waves with an electromagnetic counterpart. So this is what we call multi-messenger astronomy, where you get the same message from different sources or from different information. The clearest example of this is if you have two neutron stars crashing together. Not only are these going to produce gravitational waves, they're also going to produce a burst of electromagnetic radiation. This is a burst of energy that we can see with our standard telescopes, with our usual optical redshift X-ray telescopes. So what you hope to happen here is that you will get both the gravitational wave signal and also the flash of light in the sky coming from these two neutron stars. And we already have this. We have already been able to do this once. Now, the good thing is that the gravitational waves are produced as the objects come together, but just before they collide. And the burst of electromagnetic radiation is once they collide together. So there is a very, very slight difference between them, small but substantial. So what happened with this binary neutron star that we've actually measured, LIGO and Virgo detectors found these gravitational waves in their system that looked like neutron star mergers. So they sent out a notification to optical telescopes, like, hey guys, look over there. A lot of optical telescopes, redshift telescopes, a lot of other telescopes checked. It's like, hey, look, we have a flash of light as well. Not all of them turned around to see it. The delay is very small. But then they can check their data if they were pointing at that area of the sky. And this binary neutron star merger was seen by hundreds of optical telescopes, infrared telescopes, X-ray telescopes, and by the gravitational waveform. Not only that, but then IceCube, the detector we have at the South Pole, 1 kilometer underneath the ice, is a 1 cubic kilometer experiment, which is absolutely mind-blowing. This experiment is measuring neutrinos, the tiniest particles that are zipping through you every second. When we had this binary neutron star merger, we found the gravitational wave signal, the electromagnetic signal, and the neutrino signal. This combination of the three really allowed us to gain a lot of information. One key piece of information we gained from this is that gravitational waves travel at the speed of light. Based on the delay between these two, the optical signal, the electromagnetic signal, and the gravitational wave signal, we were able to put incredibly precise measurements on the speed of propagation of these gravitational waves. And we found that these gravitational waves travel at the speed of light, up to a very, very, very high precision. And this is really, really cool because it helped cement so it helped roll out a lot of models beyond Einstein's general relativity. So there are a lot of models which ask the question of, could there be something wrong with Einstein's gravity? Is there something we're missing? Do we need to modify our understanding of gravity? These are known as modified gravity models. Hey, thanks for the award. Always appreciate it. Thank you very much there, Jeremiah. Thank you for the award. Sorry, just trying to get your name right there. So we were able to use this gravitational wave observation with the electromagnetic counterpart to show that gravitational waves travel at the speed of light. And this is something that a lot of these modified gravity models did not expect. Because these did not expect it, then a lot of them cannot explain this. So a lot of modified gravity models, not all of them, but a lot of them, suddenly became a lot less feasible with this measurement. So of course this was not the intention of gravitational wave astronomy to roll out these models, but it did roll out a broad class of models. And I want to give another example of the type of thing we can do with gravitational wave astronomy, which is something that I personally find really cool because it's very relevant to my research. So there is an ongoing tension, crisis, debate in cosmology about how fast is the universe expanding. There are several different ways you can go about measuring the current expansion rate of the universe. One way is to use the oldest light you can see in the universe, the light that you see in every direction you look, which is the leftover light of the Big Bang. It's known as the CMB. As everyone knows, I have to show the CMB at least once per broadcast. It has to be done. So this is the background light you can see everywhere you look in the universe. This is the afterglow of the Big Bang itself. And this gives us a huge amount of information about the early universe. This also gives us a good understanding of what is our best cosmological model, what we call the standard model. We can use the CMB and a lot of other things like the clustering of galaxies to come up with our best cosmological model, in which you only have 6 parameters to describe everything you see in the universe. And you find things like there is 5% normal matter, 25% dark matter, 70% dark energy in the universe. This is all contained in the CMB. You can also get an estimate of the age of the universe, the time at which the first stars began to form, and some information about the properties of inflation itself. All of this is contained in the CMB. What you can also do with the CMB is, once you have this measurement, you can ask the question of, with this measurement, and assuming my standard cosmological model called lambda CDM is correct, what expansion rate of the universe do I get? The number you output here is about 67.73 megaparsec per second per kilometer. Sorry, second kilometer megaparsec. In any case, you get a value of about 67.73. Pretty nice. Thanks for the award there. Always appreciated. So then there's another way you can measure the expansion rate of the universe, which is looking around at local galaxies and seeing how galaxies are moving away from you. And you use something known as a standard candle, so something that has a fixed brightness, kind of like a light bulb. So we can use stars of which we know the exact brightness. We can use this to get a distance ladder, so we kind of create a relationship between the amount of light we see and the distance to an object. This allows us to put a local constraint on the expansion rate of the universe. This is a completely different way. It doesn't assume anything about our standard cosmological model, but it does make some assumptions about supernova, about the metallicity, about the stars we use. But when we do this measurement, we obtain a very different value. Well, not very different. We're not talking about 5 versus 5 billion. We obtain a value of about 73.4. So on the one hand, we have 67.73 from the CMB, assuming our standard cosmological model, and we have 73.4 from supernovae, assuming certain things about supernovae and the stars we use to calibrate them. Now, of course, this might not be a problem if these have big uncertainties, but the level of precision on both of them means that these two numbers are incompatible. So the value we obtain in one case is not compatible with the value we obtain in the other. And there is a big tension between these values. One is pushing for higher values, one is pushing for lower values. There's a lot of proposed solutions to the Hubble tension. The topic is still gravitational waves, by the way. I'm going to bring it back to that. So there are a lot of proposed solutions here. One of them is maybe our CMB measurements are wrong, although we have a lot of different CMB missions that find the same as the Planck one that I showed you. On the other hand, you could say the question of maybe there's a problem with the supernovae, with the Cepheids, but this measurement has now been done in several different ways, each time taking out different elements. Like, let's change the supernovae for something else, let's change the Cepheids for something else, and they also consistently find the same value. And then there's the other big question of, do we need to change our assumption? And one assumption we can change here is our standard model of cosmology. Now, this is where we play the fun game of how can I change my standard model enough to get the correct expansion rate, but not too much so as to mess up absolutely everything else that we've observed in the universe. We don't have the answer to this. This is ridiculously difficult. This is essentially what I did most of my PhD, is play the game of, does this new model work? Does this new model work? None of them do. So what we really need now is a whole new independent way of measuring the expansion rate of the universe. And now I'm going to tie this all back to gravitational waves, because if we observe binary neutron stars and we get the gravitational wave signal and the electromagnetic counterpart, as I explained before, this allows us to put a measurement on the expansion rate of the universe. So far we got one of these events, and we were able to find a value that is along the lines of 70 plus minus 20. This means that they found the expansion rate is somewhere between 50 and 90. It's like, thanks, this is not very helpful. But it is an amazing starting point. This was just this one data point. And it's expected that if we have around 15 of these data points, we will be able to put a constraint on the expansion rate of the universe that is of the same precision that we currently have from Planck and from supernova data. And this is a whole new way of looking at it. It's independent of CMB, it's independent of supernova, and very interestingly, it's independent of the standard model of cosmology. You don't put in any cosmological model here, which means this will really help us understand the Hubble tension. So this is a very long answer. The question that I'm answering here is, what does gravitational wave astronomy hope to accomplish? It's going to expand our knowledge of black holes, it's going to expand our knowledge of neutron stars, it's going to expand our knowledge of how these all work together. It's going to expand our knowledge on things like the Hubble tension as well. It's going to help shed light on this. Once we have gravitational wave astronomy with multi-messenger signals, we can tie everything together with other things. And then there's also the thing of the LIGO-Virgo missions are just the first step. These are to look at specifically binary black holes, local within our universe type thing. So scrap that, we're always within our universe. Local, like within a close range, a couple of billion light years away only. But there's the hope that in the future we can get even more precision. We can go to even smaller gravitational waves. And here we would hope to find the gravitational waves coming from, for an example, supermassive black holes at the center of galaxies, or even inflation itself. Now, inflation is this early period of exponential expansion that we think the universe experiences, like exponential growth in the early universe. This was such a dramatic event that it's likely that it left a background of gravitational waves. Much like we have the background of photons, the background of radiation in form of the CMB, there could also be this gravitational wave background coming from inflation. So LIGO-Virgo are the first step in gravitational wave astronomy in terms of black holes. But if we want to go to smaller black holes, we need other experiments. And there is a proposal for a mission called LISA, which is going to be a space-based mission. And the idea is to launch 3 different satellites that are going to follow each other in forming an exact equilateral triangle, keeping this distance between them exact. They're going to be following the Earth, orbiting around the Earth, kind of chasing the Earth. And these will have such a level of precision that it's hoped that they might be able to measure this gravitational wave background in the universe. This is absolutely amazing. So if everything goes to plan, it never does. If everything goes to plan, LISA should launch in 2034. There's probably going to be a couple of years delay because there always is. But this would allow us to do more with gravitational wave astronomy. Of course, these are not, first you do one, then you do the other. They both work together. They cover different different parts, different aspects of gravitational wave astronomy. These are just things that we can hope to achieve with gravitational waves, but we really are just at the beginning of gravitational wave astronomy. We're still uncovering all the things we can do. We're still defining what else we can do with it. Now we've found them. We found that gravitational waves are definitely here. Einstein was right again. And now the next thing is pushing this further and seeing what else we can do with them. Where else can we take this? Can we measure this gravitational wave background? Can we measure supermassive black holes? What more can we do? And this is absolutely amazing that we're in a point in science where we're watching a field come alive, where we're watching this field. Obviously, there's been people working on this for years, getting ready for when we have the measurements. But now we have the measurements, and now we can go forward with it. And I think gravitational wave astronomy is just such a cool subject, such a fun topic to discuss. You're under the impression that gravitational wavefront could be directly used to map black holes. It can help us understand the population of black holes. The more measurements we get from LIGO and Virgo, the more we can understand not only where these black holes are in the sky, but their overall mass, their spin, their population, how many there are. So we really will understand a lot more about black holes than we do currently, thanks to gravitational wave astronomy. And thank you for the super heart of it, always appreciated. I just saw a comment there saying you learned all of this in cosmetology school. I am not a cosmetologist, I am a cosmologist. That means that I'm a theoretical physicist. I have a bachelor's degree in physics, a master's degree in astroparticle physics and cosmology, and a PhD in cosmology. I learned all of this in my studies, extensive studies, and my postdoc since then. If you're here for makeup advice, I'm afraid you're definitely in the wrong periscope, where you really don't want any advice from me in terms of makeup. But do feel free to ask any and all questions you have. I saw a comment there saying the world is flat. I'm just going to assume you're trolling and it's not a serious comment, because we have so much information and data, and we've known for thousands of years that the Earth is not flat. So if you're still at that point, I think you're in the wrong periscope. So I'm just going to assume that you're joking and trolling and not go into that topic. So I'll be online for another 5 minutes. I think I've answered all of the previous questions that were asked. So if you want to ask any more questions, if you want to, feel free to ask questions, comments, anything you want to discuss. Happy to answer questions. I'll be online for another 5 minutes. So I just saw a comment there about crazy people hearing voices, and I'm not going to go into that because that's something for psychologists or people who are trained specialists here, and obviously that is something that is not my field. I would object to calling people crazy just because they hear voices. That's a whole medical issue. But then you make the comments of, are they experiencing dark matter? And that reminds me of a very amusing comic that I saw a few days ago of the typical setting of somebody sat with a psychologist and asking the question of, so is this in the room with us now, when somebody experiences something weird? And the question was towards a physicist, so is this dark matter in the room with us now? And I did find it very amusing. It is a funny take. I'm just going to assume that your comment was aimed in this general direction. And we don't have any direct evidence for dark matter, so it is a valid question of, are we just crazy dreaming up something that we can't see? But we do have a lot of indirect evidence for it. We have a lot of observations in our universe that we haven't been able to explain without dark matter. We have observations of how galaxies merge, of how stars move around in galaxies, of how clusters of galaxies crash together, and of course the CMB. And when you put all of this together, we haven't been able to find a better model than dark matter to explain all of these things. You might be able to explain, for example, rotation curves with a model that doesn't have dark matter. But to explain the CMB, the rotation curves, the galaxy clusters, the lensing, all of this together, you really do need something that works as well as dark matter, because dark matter is the best model we have. So I know that this might not necessarily have been where you were heading with the question, but I don't think we're randomly grasping at straws here for dark matter. It is currently the best explanation we have. That doesn't mean it's the correct one. Science is constantly changing, adapting, adjusting, and improving based on observations. If you find an observation that is different to what we currently think of being reality, then we have to change our definition, we have to change our theory, we have to change our models. Dark matter might not be the answer, but it is the best one we've been able to find so far. And until we find a better model, we will stick with dark matter. But of course, that doesn't mean it is true. It is absolute that dark matter definitely exists. It's just given everything we've seen currently, we think dark matter is the most likely explanation. We might have to revisit that if we find new data, or if we never find dark matter, or we might have to revisit this assumption if we find a better explanation. But currently, dark matter is the best we've been able to come up with. Is there a forum you're on that you will answer more long-winded questions? When I initially started my broadcast, which is about 6 years ago now, almost 7 years ago now, I also started a blog with the idea of I could answer questions on my blog. Now, the problem is I had lots of ambitious ideas for my blog on 0 time, so my blog is kind of dead. I can tell you that I have a few blog articles half written or mostly written, which will be out soon, but I'm purposefully leaving the interpretation of soon very vague. At some point, I will resuscitate my blog. But if you do have really specific questions that you think might be too long to discuss on Happs, you can reach out to me on Twitter. My Twitter handle is the same as on Happs. That's at DCHooper91. My DMs are open. Please don't make me regret that. I do get some nasty messages, but most of them are overall nice. If you have a specific question or a topic to discuss, you can reach out to me on Twitter. If I think it's a super interesting question, I might even do a Twitter thread about it, like, oh, someone asked me this, let's discuss it more. I currently don't really have a forum. I thought at some point of joining Reddit, didn't work out. So yeah, if you have a specific question, the easiest way is to check if I've answered it on my blog. And if not, just send me a message over Twitter, and I'm happy to discuss it further with you. And if it's a great question, I'll find a way to put it out there. Maybe I'll make a blog post about it if I ever go back to doing that. But yeah, do feel free to reach out if you have any questions. I'm not sure if you can send each other messages on Happs yet. I'm not sure. I think you can write comments on my profile on Happs maybe. So, feel free to reach out on Twitter and I will try to answer your questions there. Lambda CDM cosmologists, mon-cosmologists are crazy people who hear weird stuff, and I'm pretty sure mon-cosmologists say the same about us. So Lambda CDM is our current best-fitting standard cosmological model. It's what we call like our standard cosmology model. And MOND is modified Newtonian dynamics. It tries to offer an explanation that doesn't invoke dark matter. There's often a lot of rivalry, mostly fun rivalry, but also a bit of rivalry between these competing fields and competing perspectives. Lambda CDM, I'm a Lambda CDM person. I'm going to say Lambda CDM has a lot more evidence than MOND. A Mondian would call me crazy. So, there's always different opinions on the topic, and it is fun. It is fun when you put a Mondian and a Lambda CDM-ian person together and watch them debate. It's always very entertaining. Okay, I see a question here that could be fun to answer. Is it true that as we only know the size of the known universe and not what the real size could be, that everything related to that will only ever be theory? So just to clarify here, when we use the term theory in science, we don't mean something crazy that we just dreamed up that we don't have evidence for. If you wake up one day and see the wet floor and you say, I have the theory that it rained overnight, that's not a theory, that's a hypothesis. A theory is something that has a lot of evidence, facts, and observations that support it. A theory is the best we have in science. We don't call them facts because we might be wrong, because we might find evidence at some point that will change this. But a theory means it's passed every scientific method, it's passed all of our tests, it gets the gold star in science. A theory is the best we have. So I just want to clarify that there, because we often use the word theory different when we're speaking colloquially, as in physics. So this leads to confusions, because then we talk about the theory of general relativity, which is one of the most well-cemented, well-studied theories. This does not mean it's a crazy hypothesis, as we would use the random word theory to describe pretty much anything in colloquial speak. I just want to make the distinction there. My regulars know that's a pet peeve of mine. So as to your question, which is a very nice question. So all of the observations we do, all of the information we gain is limited to our observable universe. And our observable universe is a sphere centered around us. I'm not saying that the universe is centered around us, just the observable universe is a sphere centered around us. And this just marks the region of space and time that has had time to send us information. We know that there is a maximum speed that things can travel in the universe, which is the speed of light. And we know that we know that the universe is finite. So if you combine the finite lifetime of the universe with the finite speed of travel of light, you get to the point that there are things really, really, really far away in the universe that have not had time to send us information. Given that the universe is now expanding and this expansion is accelerating, these regions of the universe will never be able to send us information. So everything we measure, everything we study, everything we can investigate is within our observable universe. And then we make the assumption that we're not in a special or privileged or unique region of the universe because we're not that egocentric anymore. And therefore, what we see is probably a good sample of the universe at whole. But everything we do, everything we discuss, everything we study in cosmology is contained to the observable universe. We cannot go further than our observable universe by construction. So anytime we say the size of the universe, the age of the universe, we are always talking about the observable universe. And then we make the further assumption, our observable universe, the sphere around us, is not special. We're not in a privileged position, and therefore what we see is a good impression of everything else out there. This might be an invalid assumption. It might be that our observable universe is unique, and anything outside of the observable universe is different. But as you say, we cannot see outside of our observable universe, so any claim we make is always limited to the observable universe. Okay, I think that was a really nice question and a good question to end my broadcast on. I've been online for just over an hour. As always, this was great fun. Thanks a lot for the questions. We had some fun topics and fun questions. In case you missed the beginning of the broadcast, tomorrow there's a rover set to land on Mars. It's going to be amazing. You want to tune into the live broadcast tomorrow at 2:15 Eastern Standard Time, 8:15 in the afternoon Central European Time. NASA will be broadcasting live. You'll get all of the updates, all of the information, and you'll get to follow along with the amazing thing that we have of a rover hopefully landing on Mars. Definitely tune into that tomorrow. It's going to be amazing. So thank you everybody for joining. I am trying to get back into a habit of doing broadcasts regularly. I used to do broadcasts once, even twice a week. I'm trying to get back into that. So I'm currently trying different times. I'm not sure if I will stick to weekends or weekdays. It seemed like today it was kind of quiet, but also lots of nice questions. So my point here is that I will be online again at some point during the next week, but I'm not yet sure when. This would not be my regular time for sure, because Wednesday 6 p.m. is technically for the TTK, my former institute that used to do periscopes. I'm not actually sure if they will go back to doing broadcasts at some point. I hope so. Once I figured out my regular time, I will let you know. If any of my regulars really have lots of constraints, just message me on Twitter, not email me. Message me on Twitter and say, like, please don't do your broadcast at this time slot, and I'll try to avoid it. Obviously, I can't accommodate everybody, but just let me know if anybody has preferences. But I will try to fix a regular broadcasting time to go forward. It helps me keep them regular. So I'll be online at some point next week. I will announce it about 24 hours in advance. If you follow me on Happs, you will get the automatic notification. So be sure to follow me on Happs if you want to catch all my future broadcasts. So thank you everybody for joining. I hope you enjoy the rest of your evening or afternoon, wherever you are. I hope to see you again soon, and I hope that in the meantime you all stay safe and take care of each other.